I'd like to welcome you all together to the Design for X session. Maybe 2 words about my person. My name is Stephan Husung, and I'm the chair of Product and Systems Engineering Group at Technische Universität Ilmenau in Germany. We also do a lot of work in the field of Design for X, and especially today, I'm very happy that we have 5 very interesting topics with a lot of different X in the Design for X field. So I'm very happy that you present today your ideas, and that I hope, and in the end, I hope that we will have a very interesting discussion afterwards. Maybe some words at the beginning. Robert, you will make some extension if necessary. It would be good if everyone who is not presenting is switching off the microphone and the camera at the beginning. We can activate if necessary during the discussion. But especially during the video presentation, it would be good if only the presenting authors have activated the camera. The microphone should be switched off for everyone. Robert, I think you have some more informations.
Okay, just one more time. I will play all 5 presentations one after the other. If you have any questions during the presentations, please use session chat to write them down. After all 5 presentations, the discussion will start. That's everything from me. I will start now. Is it okay, Stefan?
That would be good, yeah. If no one else has a question, I think there's one question in the chat. No, I think we can start with a video. Thank you.
Hello everyone, my name is Patrick Hommel and I would like to present you our contribution about a method for evaluating the applicability of aluminum foam sandwich. Sandwich materials have a great potential for lightweight design, especially aluminum foam sandwich, which consists of aluminum alloys in the face sheets and also in the foam core. This material has many benefits, for example, a low density at a high bending stiffness and good energy absorption properties. It is also completely recyclable. But even though AFS has many advantages, the number of industrial applications is relatively low, for reasons such as a lack of design knowledge or a lack of reference applications. Often the designers do not know where the material could be used profitably. If AFS is excluded from the selection process without evaluating of its suitability for the use, the potential of the material may not be realized. Because there is no support for the selection of AFS components, the aim of this contribution is to develop approaches towards a method which helps to evaluate if the use of AFS is reasonable for a given application. Therefore, the main research question of this paper is, how can a designer be assisted in deciding whether it is appropriate to use aluminum foam sandwich instead of a reference material in an application? Let's first take a brief look at the state of the art. A well-known approach for material selection is the method according to Ashby. Here, relevant material properties are derived from requirements so that materials that do not meet these required properties can be excluded. Then a ranking of the remaining materials can be made and additional information can be used to select the most suitable material. A variety of databases and different material diagrams exists for this procedure, which provides the basis for the evaluation. However, it is remarkable that the diagrams do not include aluminum foam sandwich or even aluminum foam as a single material, as shown in this example. Now, the obvious step would be to include AFS in these diagrams. To a certain level, this can be done, but it is not possible for all diagrams, because not all material properties of AFS are known. If you now look at these 2 diagrams, the corresponding properties are partially known, so a new diagram with AFS could look like this. However, there are some challenges here as well. This can be seen in the fact that the AFS markings are not a single point, but rather cover an elliptical area. This is due to different sandwich configurations, such as different layer thicknesses or densities. The main problem is that some characteristic parameters are not known or vary so much in investigations that no quantitative comparison with AFS would be possible with these existing methods. The chosen approach of this contribution provides a more qualitative comparison. Different criteria are given points so that the advantages and disadvantages of the different materials can be determined, and the ranking is possible. It is also necessary for the method to consider different materials and different material requirements, depending on the use case. As a basis, a table in which properties of individual materials are evaluated semi-quantitatively can be filled in as shown here. With this material matrix, an evaluation can be made later. In order to illustrate the procedure of this method, a case study is used. For this purpose, an extendable step of a train is selected. In this case, the step is made of aluminum. In order to reduce the energy costs, the aim is to determine whether a reduction of the moving mass is possible by replacing the step with AFS. The procedure is as follows. First, the materials to be compared are selected. In this case, aluminum is the reference material and AFS is the material under review. Next, relevant requirements are selected. For example, the entrance area of a public transportation system must bear a lot of load and needs high mechanical properties, and also must be corrosion resistant. Appropriate requirements can then be selected in the program. Finally, an automatic calculation of points takes place for the user, based on the previously stored values of points. In this case, the total result is a ratio of 27 to 24 points. This indicates that the use of AFS at this point is suitable in principle and has advantages compared to aluminum. The advantage of this application is its simple and intuitive use. In addition, no expert knowledge of the material is necessary for the user. The designer only needs to define requirements and materials in order to quickly obtain a result and gets a first impression about the appropriate use of materials. A possible prototype of the step made of AFS is shown in this picture on the right. So in conclusion, AFS is rarely used because of a lack of supporting methods. Due to fluctuations in material properties, comprehensive quantitative evaluations of these properties cannot be made. This is why a qualitative method has been designed. The selected method is an evaluation table in the form of a checklist and serves to assess which material is best suited for the use case. A corresponding approach was presented in the last minutes and can be considered in more detail in the paper. In the next steps, a two-stage process is to be elaborated, in which a rough evaluation is followed by a second, more detailed evaluation. However, this requires further research and investigations so that the method can be developed in its entirety and implemented digitally. Thank you for your attention and enjoy the conference.
Hello, my name is Arindam Brahma from Chalmers University of Technology in Sweden. I'll be talking about the paper my colleagues and I are presenting in this conference titled Use of Margin to Absorb Variation in Design Specifications, an Analysis Using the Margin Value Method. Before we jump into the main content of the paper, I would like to give you all a brief introduction on why design specifications might change. Changes can be because of many reasons. Customer requirements could change, a company might want to reduce costs, or perhaps improve the design. Changes could be triggered by changing legislations, and so on. But changes such as these often tend to have significant consequences, commonly known as knock-on effect. That is, when you initiate a change in one component, a chain reaction occurs and the designer finds that as a result of changing one component, a lot of the other components have changed, somewhat like a domino. However, designs are of course not linear and are much more complex than a linear domino. Designers often overspecify components to handle these sorts of changes. These overspecifications are sometimes called design margins, which are like shock absorbers. If a change is initiated, these margins can potentially absorb them so that the knock-on effect is minimal. It is important to note here that the extent to which the absorption happens is related to the amount of margin available. However, margins are neither equally spread nor are completely consumable or comparable. Some margins can be in, say, newtons or kilograms, while some others might be in a completely different unit, say time in minutes or seconds. So comparing them can be challenging. A method called margin value method, or MVM, was developed to solve some of these issues, mainly in localizing, sizing, and allocating appropriate margins in design. The MVM, or margin value method, starts by looking at the design problem as a network, which includes some input parameters, design decisions, and resulting performance parameters, which can be set up as required. The method involves calculating three metrics. Firstly, the local excess margin, which is to identify how much margin each component has. Then impact, which is to quantify the undesirable effects of margin on performance parameters. And finally, the third metric, which is absorption, which relates to the amount of absorption possible in each margin node for a given variation in the input specification. For this paper, we demonstrated the approach using a belt conveyor case study. The margin analysis network is shown on the right. The orange diamonds show the specification parameter which are likely to vary and therefore are of interest. The large diamonds are decision nodes, the circle are calculation nodes, and the red donuts are performance parameters. Conceptually, if all the specification parameters are varied depending on an expected distribution, it could be in theory be possible to create designs which perform well against variation. Conceptually, there would lie a zone where change gets absorbed, a zone where the changes are not absorbed and are left underutilized, while there will also be a zone where sufficient absorption capability does not exist and the change propagates. Similarly, for impact, there could be zones of high impact and low impact. Low impact of low probability is obviously preferable. This slide shows the absorption potentials and deteriorating impacts of all the margin nodes in the conveyor case. For clarity, let's look at the margin node E1. This plot looks at the margin node E1, analogous to the conceptual plot presented before. The red portions are places where change propagates, while the blue portions are where the variation does not cause a propagation. The ideal design would be if no propagation happens, while the undesirable impact of the margins on the performance is also fairly small. To reduce the probability of change propagation, there could be two strategies. Firstly, once the bounds where change propagates is known, the variation in input specification is reduced. For instance, such a reduction causes the probability of high impact to drop to a lower probability of low impact. The absorption potential on the graph on the left also shows a reduction in propagation probability. A second strategy to reduce propagation could be to allocate extra margins wherever needed. Here, note that adding margins indiscriminately may not be helpful. There are these limiting cases which cause margins to remain unutilized to a large extent. For instance, you can see that absorption potential does not increase when margin is added only to E1, but increases when added to E3 as well. This can be seen on the graphs on the left. For contributions, we demonstrated that it is possible to apply the MVM approach to determine probability of change propagation. We suggested two strategies: restriction of input specification and allocation of larger margins to reduce the probability of change propagation. We also demonstrated that there could be limiting cases where margin allocation doesn't help. We also discussed that a ratio of undesirable impact to absorption capability could be set up, which could be used as a decision support for design managers. The method also has some limitations. The method can be cumbersome to set up, especially the margin analysis network for a design. The approach at the moment is analytical, but will be developed as the method evolves in the future. The performance of components has not been taken into account. Performance, as we know, may deteriorate with wear and tear. The example which is used is limited. A large number of margin nodes may be difficult to be analyzed at a given time. We, of course, would continue the work to address these limitations in the future. Thank you.
Welcome to the presentation of our contribution named Uncertainty Analysis of a Calculation Model for Electric Bearing Impedance. My name is Peter Welzbacher. I'm a research associate at the Technical University of Darmstadt in Germany at the Institute for Product Development and Machine Elements. Let me start off with a quick introduction and the motivation for our research. Due to Industry 4.0 and the implementation of cyber-physical systems, a substantial need regarding information about relevant state and process variables of technical systems arises. Sensing machine elements, like the sensory utilized rolling bearing shown here, enable the measurement of these variables in a technical system. Sensing machine elements build upon the primary mechanical functions of conventional machine elements and enhance them with sensory functions. The quality and reliability of the data provided by these machine elements, however, heavily depend on their underlying calculation model and the associated uncertainty. The calculation model describes the relationship between the provided measuring signal and the measurand. For the analysis of uncertainty, there are already some frameworks that are theoretically applicable. However, since these frameworks were developed against a different background, it remains unclear if and how they can be applied to calculation models of sensing machine elements. Consequently, the aim of our contribution was to investigate if and how an existing framework can effectively be applied to the calculation model of a sensing machine element. Therefore, we considered the sensory utilized rolling bearing as an example. Before we take a look at the uncertainty analysis of the calculation model of the sensory utilized rolling bearing, let me give you a quick introduction on how the bearing works. The sensory utilized rolling bearing allows the measurement of the load applied to the bearing by its electric capacitance. Therefore, the inner and outer ring are contacted and an electric voltage is applied. The bearing is now considered as a network of capacitors as shown in red in the right figure. On the one hand, the total capacitance of the bearing results from the capacitances of the loaded rolling contacts. In the fluid friction regime, in which rolling bearings are operated in many applications, a lubrication film develops which separates the loaded rolling elements from the race. Since bearing lubricants typically have a high specific resistance, only minor direct current passage will occur. Consequently, the capacitance of a single loaded contact can be calculated as shown in the yellow box, taking into account not only the capacitance of the heads and contact ellipse, but also the capacitance of the remaining area within the groove. On the other hand, unloaded contacts also contribute to the total capacitance of the bearing. The description of their capacitances is quite complicated since they depend not only on the overall displacement of the inner ring, but also their position within the bearing and many other factors. As a result, the overall correlation of load and capacitance of the bearing, and thus the calculation model, includes a multitude of input parameters, domains, and dependencies, which makes it not only quite complex and nonlinear, but also susceptible to uncertainty. The methodical approach we applied for the uncertainty analysis of the calculation model of the sensory utilized rolling bearing is based on the approach developed by Vorwerk-Hanning et al. And consists of 4 consecutive steps. In the first step, the uncertainty occurring in the calculation model is identified. Therefore, the context of the sensory utilized rolling bearing is analyzed in the first place in order to identify disturbance factors that may influence variables and parameters included in the model. Subsequently, the input parameters of the calculation model are analyzed regarding a temporal variability, dependencies on the pre-identified disturbance factors, and associated measuring uncertainty. Finally, the calculation model is checked for inadmissible simplifications and assumptions. In addition, the model is analyzed with regard to not included relationships between occurring disturbance factors and variables or input parameters of the model. In the next step, the identified uncertainty is evaluated using 3 different criteria: severity of the uncertainty, deviation of the uncertainty affected variable or parameter, and the impact of the uncertainty affected variable or parameter on the output of the calculation model. In order to ensure the consistency of the evaluation, rigid schemes were developed and applied. Based on the evaluations assigned to each uncertainty during evaluation, a reasoned decision can be made whether an uncertainty is critical for the quality and reliability of the provided data or not. If an uncertainty is considered critical, measures for its reduction or elimination are developed in the last step of the methodical approach. So, what were the results of the uncertainty analysis of the calculation model of the sensory utilized rolling bearing? First of all, we found the initial approach for uncertainty analysis by Vorwerk-Hanning et al. In principle applicable to the calculation model of the sensory utilized rolling bearing. However, some adaptations had to be made in terms of the therein included methods and tools in order to be able to apply these to the calculation model of the sensory utilized rolling bearing in a meaningful way. Especially in the evaluation of identified uncertainty, adaptations had to be made since the originally defined evaluation criteria were only partly transferable. In the course of the uncertainty analysis of the calculation model of the sensory utilized rolling bearing, we found that of the 4 uncertainty affected input parameters that we exemplarily considered in our contribution, 3 are critical for the quality and reliability of the data provided. Furthermore, of these 3, 2 required measures to be developed in order to reduce or eliminate their associated uncertainty, and thus ensure the quality and reliability of the data provided by the sensory utilized rolling bearing. Let me end my presentation with a brief outlook. In the next step, the development of a general framework for the systematic derivation of measures to manage uncertainty is targeted. In this context, it is conceivable to use the valuations previously assigned to each uncertainty as a starting point for the derivation of effective measures for their elimination or reduction. Subsequently, an analysis is planned to investigate the extent of transferability of the adapted approach to calculation models of other sensing machine elements. This brings me to the end of my short presentation. Thank you very much for your attention and the interest in our work.
My name is Pekka Uski. I'm a lead engineer in mechanical engineering in a company called Etteplan. And I'm also a PhD student in Tampere University in Finland. My supervisor is Professor Asko Ellman. Our title of paper is Model-based definition accelerates product lifecycle in manufacturing and inspection phase, experiment of machine 1 of production. Our research bases on findings in manufacturing operations in Finnish companies. This experiment relates to the research that was done during 2019 and 2020 in the manufacturing ecosystem. Our research question is how much time can be saved in implementation of different level of MPD and manufacturing and inspection phase of one of production of a machine part. One-off and small series production is common in Finland, which is focus area on my studies, and that's why we selected one-off production in the topic of this paper. Setup time, including programming, takes large share of one-off production life cycle. We found out that levels of product definition are 2D drawings only, that is called drawing-centric definition. Primary 2D drawings with supplemental 3D model. A primary 3D model with supplemental 2D drawings, which is called model-centric definition. And 3D model without 2D drawings, that is model-based definition. We wanted to find out, is there possible to save time on the manufacturing and inspection phase of machine part using different levels of product definition? We know that there are 3 kinds of levels of product definition that was used in manufacturing ecosystem. Our test parts have different complexity, and here we can see 2 kinds of parts which have a different number of manufactured features. This procedure of this paper is that the manufacturing and inspection test was performed in following order. First, by using 2D drawings only, drawing-centric definition. Second, with 3D CAD model and 2D drawings as supporting material, model-centric definition. And with 3D PMI annotation model only, model-based definition. And here we can see the part number 2, which includes 3D annotations, so-called PMI information. We got results in transforming from model-centric definition to model-based definition that manufacturing time was same because CAM programming with MPD is still limited. MPD helps CAM programming, but automatic CAM programming is little utilized. However, inspection time was reduced due to automatic sim programming, which is enabled by model-based definition. When we compare parts 1 and 2, we can find out that manufacturing time in part 1 was same with model-centric and model-based definition. Inspection time savings was significant with model-based definition, where time saving was over 40%. And in part 2, manufacturing time was saved about 1%, and inspection time was also significant. Saving was 56%. And we can see that when complexity was increased, also manufacturing time was reduced with the definition by models. And this was our paper's content, and I want to thank you your attention.
Hello together. My name is Lea Strauss and I'm a research assistant at the University of the Bundeswehr in Munich. In the next minutes, I'd like to present you the effect of heat treatment on the hardness of unconventional geometrical features for laser powder bed fused aluminum, here ALSE10Mg. First, for the ones that aren't yet familiar with the process of PBFLB, I'd like to explain the process shortly. Metallic powder is put from the left chamber on the building platform seen on the right. Here, a laser beam melts this layer and also partly the layer below, so that a connection of these layers is present. Afterwards, the building platform lowers and a new layer of the powder is put on top. So like this, a three-dimensional part is generated layer by layer wise. This manufacturing process implies benefits like more significant freedom in design, especially compared to conventional manufacturing processes. PBFLB of our lightweight aluminum proceeds under conditions like a high melt pool temperature, a high cooling rate, and a high thermal gradient due to the laser beam. This results in a fine microstructure and therefore high strength, but also a low fracture strain. Additionally, anisotropy, residual stress, and process-induced pores occur. Therefore, we have a reduced fatigue strength, meaning a short lifetime is present. But if you apply additionally thermal post-processing, anisotropy and residual stresses can be diminished. As a thermal post-processing, different processes can be applied. For our aluminum alloy, T6 is recommended. This procedure involves 3 steps. First, solution annealing, followed by quenching and aging. And here, the microstructure changes. On the one hand, the silicon magnesium dissolved, what leads to an increase in strength. And also on the other hand, the microstructure gets homogeneous. I already mentioned previously that additive manufacturing of our aluminum leads to a fine microstructure. So therefore, in order to dissolve the grains, a short-term heat treatment should be performed, what is also an economical benefit. In our study, we evaluated the effect of a T6-like heat treatment on unconventional geometrical AM features. And the aim was to investigate the effect on the hardness. For this, we took a closer look on this piston. This is a piston from a Ford block engine. Before the post-processing, different design modifications following the spare part design methodology were performed. For example, the section here, which serves as a structure to connect the pin boss with the piston head, was topologically optimized to resist a cyclic load at a reduced volume and also a predetermined center of mass. Furthermore, the structure contains the lattice structure, as the increased complexity comes at no additional manufacturing expense. The piston was built in an upright position as depicted here. And here, of course, support structures on the inside were essential. Here we chose tree-like support because this leads to a good heat dissipation. After this, a T6-like heat treatment was performed. Here you can see the temperature profiles of the furnace and the piston. And finally, here you can see the result. In addition to the effect on the hardness, we also wanted to figure out how can designers take advantage and exploit DFAM knowledge on thermal post-processing. Here are our results. We performed different viscous hardness measurements at various spots. For this, the piston was cut into several slices and polished before measuring. For the profiles A to D, the effect on the heat treatment on different wall thickness can be seen. For A, the hardness decreased slightly from the outside towards the inside. A similar behavior was detected for the profiles B to D. This consistency implies no effect of the topological optimized section on the heat treatment process or the hardness. Then profile E shows the influence of the tree-like support structures on the hardness. Compared to the previous profiles, a more homogeneous hardness is present. This implies that a support structure next to this section, while on the inside of the piston, had no significant effect on a T6-like heat treatment and quenching. The outliner here might occur as a harder silicon structure might be located at this measurement position. Then the hardness of the topological optimized structure, the profiles showed a promising homogeneity despite the large wall thickness. It seems like that heat treatment and quenching can perform pretty good for the lattice structure, which is used to fill the gaps in the piston design. Overall, to answer the first research question, the T6-like heat treatment reached good, yet not optimal homogeneity reflected as a gradient on the hardness profile across the tested surfaces. First, an influence on the wall thickness on the resulting hardness was detected. Second, the topological optimized section showed no effect on hardness, as similar values were estimated. Also, the support structures lead to no negative effect on hardness, as heat treatment and quenching was able to be performed homogeneous. Then, the inner lattice structure also showed promising results, as a homogeneity in hardness was detected. As a consequence of our study, we concluded following regarding our second research question. How can designers take advantage and exploit DFAM knowledge on thermal post-processing? Well, when thermal post-processing is performed on AM aluminum, we recommend first, in order to avoid barriers for heat transfer like quenching, tree-like or pin support structures should be used. Also, you should bear in mind that large cross-sections diminish the effect of heat treatment, especially for quenching. This should be taken into account, particularly for topological optimized bodies. In addition to this, lattice structures lead to homogeneous properties as the quenching medium is able to infiltrate the inner lattice properly. This demonstrates the ability of the lattice structures to dissipate the heat during quenching. Last but not least, it's possible to apply T6-like heat treatment to fully enclosed lattices, as the cooling medium reaches the inside via the depowdering holes. Here, the heat transfer is comparable or likely better than for the solid sections. So if you have any questions about our study so far, please let me know. And by now, I just can thank you for your attention.
So, thank you to all the presenting authors for preparing this very interesting videos. Now we have about 40 minutes time for discussions. As I wrote in the chat, I think it would be good if you wrote down the question in the chat, or maybe some words about your question, and then we can discuss them here together. Currently, I don't see any questions, so maybe I start with the first questions from my side. I have a lot of questions. I had the possibility to see the videos and read some of your papers before the session. Maybe I can start with the first paper. Maybe one question to Robert. Should we now move everyone to the moderator level in the session?
If somebody asks to share audio and video, we can move.
Okay. Otherwise, it's not necessary.
Otherwise, not necessary. Yes.
Okay, that's good. Okay, so I come back to my question. I start with the first paper with the aluminum foam sandwiches. This is very interesting, especially also in Ilmenau. We have some research in this field, not in my group, but in the material sections. They work with metal foam, not with aluminum foam. And here always we have to discuss that not only the material properties have influence on the selection, but also the design guidelines. For example, how to manufacture it, how to guarantee the other properties you need, for example, lifetime properties, stiffness, and so on. Did you also consider such properties in your research?
Yeah, thank you for the question. I consider more the aspects of the later parts, so not of the manufacturing, more about the joining techniques, or how you can bend the material, and what kind of solutions are for hybrid material combinations, but not on the manufacturing part.
Yeah, especially at the end product, you have a lot of properties you have to consider.
Yeah.
I know also from the colleagues in Ilmenau, they have a lot of challenges in the field of reproducibility of manufacturing, so that you can guarantee the overall product properties. And this is still a challenge when you go to industry to transfer this. I don't know if you have the same challenges in your field.
Yeah, of course. The industry is always critically when there are no clear properties, and there are some the parts are varying a lot, and there are some different challenges in different parts.
Yeah, that's very, very interesting,
Yeah, it's
especially
interesting that you also have some researchers in this topic, so maybe I can.
Yeah, I can bring you in contact with our colleagues.
Sure.
Maybe you can change or exchange some information.
Yeah,
very good.
Would be great.
Someone else. I think it's not the idea that I am the only asking one. I have a lot of questions, but I think it's a session where all of you can ask. If not, I come to my next question. Please add your questions to the chat so we can discuss them together. Then I have a question for the second paper. I like this idea. I know similar work also in the field of robust design, because there we also discuss what are the impacts of some changes and so on. And especially in this context, my question is, which types of margins did you consider in your work? In the paper or in the presentation also, I see primary geometrical margins. Do you have different types? I also can think about material margins or other ones. Which types did you consider?
So that's a very good question. Thank you for it. I'll say that all types of margins needs to be considered, because they all it actually depends on how you're defining the performance criteria of your design. So if your performance criteria, for instance, relates to weight, it needs to be lightweight or something like that. Then of course all your margins, whichever affects weight, needs to be considered. So that's the first thing. So we cannot ignore any types of margins. To elaborate further, the method actually looks into that as a gap, that not all margins are comparable. So we did develop the method in such a way that they can be compared in some form. To elaborate it even further, we actually classify margins into two types. We say one of the types is deliberate margins, and the other type is the margins which are put in inherently with the design. So deliberate margins are like safety factors and stuff, which are charged on the design, while the other ones which come inherently by faulty optimization and stuff like that. So we look at margins in that ways rather than it being geometrical or any other kind. We do not discriminate.
Okay, that's interesting. Before we come to the question in the chat, maybe one additional question in this field. Did you also consider which influence has a margin maybe on other product properties? If you add some margin, especially to reduce one effect, then you also have to think about what is the impact on the other properties. How did you realize this?
Absolutely. So that's why we define the performance parameters at the start. So once you define your performance parameters, you can see the impact of the margin on those performance parameters. So that's we do account for that in our method.
So the focus is on the performance parameters
absolutely
that are relevant for your design.
Yes.
Okay, very interesting. Then maybe we make a switch to presentation 5. Felix, you have a question. Maybe you can ask this. Is it possible that, Robert, is it possible that Felix can ask?
Felix needs to ask for audio and video in order to let him to share. So maybe, okay. Felix, here you go.
Felix, we cannot hear you. I see you. I think.
You hear me now?
Yeah, now it's working.
Okay. Thanks for the nice talk. My question is for talk number 5. Interested in.
Do you have something like microphone? You have a lot of disturbances.
Okay.
Please come closer to the microphone.
Closer to the microphone. Maybe that's enough.
Okay. Now it could work.
Yes.
That's good.
Okay, perfect. My question would be how we could reduce the differences which we saw for the different hardness for different wall thicknesses. So could we, for example, increase the time that we heat the different samples, or is there any parameter we can change that we get rid of these differences?
Yes, thank you for the question. We can decrease the difference when we increase the time or also the temperature of the heat treatment, but there we also have a problem if the temperature or time is too high, respectively too long. The hardness decreases for the thinner parts. So we have to decide whether we want good results in the thin parts or in the thick parts. So there's a huge difference.
Okay, thanks. And maybe one more question. Is there also some chemical or so we could add while heating the probes for aluminium? I only know for iron, for example, that we could add, for example, some coal or something like this, or carbon, that the surface gets even harder. Is this also done with aluminium?
To be honest, I'm not sure if someone did this before. I think it's possible, but we didn't perform this as the normal T6-like heat treatment is recommended in a general oven with under air conditioning.
Okay.
Okay, thanks.
So, very interesting. Someone else has a question about this? Otherwise, I have a question also for Peter. Now you are back in the session.
Yes.
Yeah.
With my internet, I think.
Yeah. I also had the same problem during the videos. My browser was frozen. I had to log in again, I think.
Oh, it's working. At least I hope so.
That's good. We waited for you. Everything's fine. Also, very interesting presentation with the models to identify or to handle the uncertainties. On your slide, you have you presented a 4-step methodology, and the last step was to develop measures. My question was in this field, how do you want to develop them in detail? Because you also have to identify what is the influence of your measures on other properties. How do you do this in detail? I didn't see it in the presentation.
Yes, that's true. First of all, thank you for your question. This is quite still an open challenge because in the contribution, the development of measures to eliminate or reduce uncertainty were developed on intuition, or maybe you can call it experience. But we are still working on a framework to systematically link the evaluations to effective measures to reduce or eliminate uncertainty. So, yeah,
But this means something like predefined measures, or something like catalog of measures you can use, or
yes, some more in the direction of general approaches. Like if the deviation of a quantity cannot be quantified, then you have to generate information in the next step in order to be able to address this uncertainty and answer the question if it is critical or not. And if you arrive at that level of information that you can say that an uncertainty is critical for the reliability and quality of the provided data or not, then you can start to develop measures.
Of course.
If you start at this point, you have to consider a multitude of different points like if it's caused by a disturbance factor, you have to consider the origin of the disturbance factor. If you can just shield your sensing machine element or sensory function, or maybe you can add different sensors to measure the disturbance factor and then get rid of it in the post-processing.
Yeah, that's right. Interesting, yeah. Good, very interesting, yeah. We are also in contact with Eckhard Kirchner about a lot of such topics, so it's very good that you work on this. Great. Yeah.
Thank you.
Then I also have a question for Pekka or maybe Asko. I'm not sure. Is Pekka online? The model-based definition. Is someone of you? Can you hear me? Asko, Pekka, can you hear us? No.
Yes, I hope that Pekka can answer on this.
Yeah, otherwise you are also the expert.
Yes.
The model-based definition topic is also very interesting, and we also see a lot of interest in research and also in industry currently. I wondered a little bit about the table with the times, not about that the production time could not be reduced so much, but more about what is the scope of the time that was presented there. Is it only the preparation of the manufacturing, or is it the manufacturing at all, which was compared there to the 3D drawing?
So we were comparing the total time from the, let's say, starting to the finishing of the process. So, and when we were considering the on-off production, which means that there are quite a lot of preparation time anyhow.
Yeah.
And I think in this kind of production, for example, making spare parts and that kind of things, this model-based definition might get the most of the profit on time saving.
Yeah.
But we found out that actually it's not really possibility to use model-based definition in CAM processing. And we found out that, for example, Siemens NX, there are only few customers in whole Scandinavia who are able to use it, and because they use very special products, that's they will employ that. But let's say in inspection phase, you can use automatic creation of the SIM code, and that actually gives you huge time saving on the process.
Yeah. What do you mean there in detail when you say there's no CAM support or computer-aided manufacturing support?
There are, but I mean, then you need to define how to make every manufacturing feature, what kind of, let's say, machining parameters you will use on that and to the specific parameter. So it means that you need to create quite big database for this. And if you are making very special kind of product, you might find it meaningful. But if you are designing any kind of product, that's work related to that is getting to be quite big.
Okay. My impression always was when I look, especially in the companies in Germany, that they try to direct use the model-based definition, for example, for the CNC programming, and maybe add some features, for example, if you have some threads or something like this, so which is not represented directly in the CAD model. So I was a little bit surprised about this, but maybe this depends on the companies you speak about. What are the possibilities they have inside?
Yeah, and it seems to be that this automatic CAM code generation is quite clumsy, to be honest. So whenever you are using a little bit more bigger series, it makes sense to really make CAM code by hand, because you can optimize it much more better than you can do it with automatic code generation. So seems to me that this is something in technology which is in let's say in development still.
Yeah. Very interesting. I have an additional question about the parts. You presented two parts in the presentation. From my point of view, they had some geometrical complexity, but more or less they are simple parts because you have regular geometry, no freeform and so on. Did you also tested some more complex parts? For example, if you have parts with freeform geometry, or if you have drawings with some special technology specifications and so on, because then I think maybe also the model-based definition could be the more efficient way to transfer the information.
Yeah. Our impression is that the more complex the part is, the more time saving you might get, and also let's say the advance of the model-based definition and having possibility to see the 3D model is getting much more useful then. These two parts were designed together with one industrial company who actually wanted to us to have a look this kind of parts. So they are not that simple as they look. They are prismatic anyhow.
Maybe.
So they we didn't try to make them too complex, but still there's quite nasty features in them which you cannot see straight away.
Yeah. Interesting. Last question from my side to your topic. Did you maybe to the other one? Please think about what additional questions you have. I think it's not good if I'm the only person asking questions. I think there are a lot of people here, and you have a lot of similarities also in your different topics. But then maybe add the questions to the chat. Back to you, Asko. Did you also consider the modeling effort? Because when we normally speak about model-based definition or compared with traditional 3D drawing workflows, we also see that there is sometimes a higher effort for generation of the 3D drawing, because especially when you have a 3D model which is not fully defined, which is typical for a lot of processes, then you have to add additional informations later to the 3D drawing. And if you have everything together at one 3D model, this also could reduce the effort for preparing the documentation. Did you also analyze this in your work?
Yeah, we have done this, and actually we know from the, let's say, literature review that it's quite much a question of how trained you are on using this additional information and model-based definition. So basically, we made some student tests on this, because for them, everything is so new, and many of them say that this model-based definition is a little bit demanding, but they think that it is for them. It's they think that they know what they are doing, because they can more easily show the surfaces that they are considering than if they would be creating 2D drawing from the 3D model and make the manufacturing information there.
Yeah, interesting. Yeah.
So also, I think we, at the future we try to have a look on this and show that let's say this is more or less on let's say matter of the generation, so that when the new people are learning this, let's say this as a routine way to make drawings, it probably get more usual. Yeah,
of course. Yeah, thank you. I think also Pekka added a comment to this. Yes, that's right. That's a geometrical complexity of your parts, which leads to a more higher effort for the production, of course. If no one else has a question, I have an additional question also for Lea. You spoke about the necessary hardness you want to optimize with your technology. We know from our research environment that we sometimes have parts where we need a specific hardness distribution, not only the full hardness in the part, only on the surface, and in the inner of the part, the hardness can be much lower. Did you also consider this in your work, or is it not necessary for the parts you analyzed?
For the piston we analyzed, we wanted to ensure that the hardness was as homogeneous as possible, because there we have the force that gets put on is pretty homogeneous during the part. So we wanted to make sure that all over the part we have the same characteristics.
Okay. Yeah, especially when we have a company close to Ilmenau, say producing shafts, very big shafts, and they only need a very high hardness on the surface, only 1 millimeter or less than a millimeter, and inside of the shaft, the hardness can be much lower. Especially they use technologies to generate this hardness distribution. Yeah, but very interesting. No one else has a question. It's the first session during the conference. Felix, you have another question?
Maybe I also have another question, again for Lea. You said in your talk that the material properties are very much dependent before you heat the parts on the direction of build. So you have different material properties from the layer structure, which comes from the process in the end. This is reduced when you do the heat treatment. But have you also looked at it for the surface hardness? If there's a difference before and after your heat treatment, and is it also reduced using the heat treatment?
Yeah, thanks for your question. We have a hardness after the printing of about 136. So based on the heat treatment, the hardness lowers really a lot. But we also have the advantages that we have a more homogeneous properties and also no anisotropy, what is really bad for the fatigue life.
So if you would print, for example, a cube and you would once measure it on top, once on both other sides, would you expect to get a difference of the surface hardness?
No, not really. Okay. But there should be a difference in so if you compare it to the post-heat treatment.
Yeah, okay. Thanks.
Yeah. Very interesting. Someone else? It's the first session during the conference. I think everyone should be fresh for the questions. Or do we need a warm-up for the conference? Maybe some additional question for the first presentation, Patrick, or Patrick, I think it's the German one. Patrick, you said you currently consider more or less the material properties in your selection. Did you also think about how to define design guidelines? Because here we're in a Design for X session, how to define design guidelines to use the sandwich structures in the overall design?
Yes, there are many different ways. First, I looked up for some other materials like metal sheets and look what are the guidelines for those materials, and then I checked if you can use it also on AFS or at sandwich. And another way is to design some products and always ask yourself what has the material look like, or what kind of rules do you have to check. So there are some you can develop the guidelines while designing some products or some case studies.
Yeah, so interesting. Yeah, very interesting. Yeah, okay, that's good. It's good to work on this again. I know in Stuttgart you also work a long time for light-right structures. I think it's also very good to place this topic there.
Yeah, thank you.
So we have a question in the chat. Arindam.
Yes, I can probably ask it myself if that's all right.
You want to ask yourself a question? No.
No. I'm asking.
Yeah. It was a joke.
I'm asking Peter.
Yeah. Peter is of course.
Yeah, so I was curious to know if there's any plans to do such analyses for multi-part components. And I'll give you a little background of why I'm asking this question is because in my method of in the margin value method, one of the things we look at is interactions of margins. And we are interested more in when there are multiple components in a design and how those margins interact, and what's the effect of one margin on the other. So such analysis, if there are multi-part analysis of uncertainty available, we might be able to include them in our approach as well.
Yeah. Peter is writing in the chat he cannot unmute itself. Robert, can we do something?
Yeah, I'm messaging Peter privately to solve the problem.
Okay. I think now he had to leave the session, or?
Usually a simple refresh of the web page.
Yeah, I think so too. Yeah.
Is the best and the fastest solution.
Now he's coming back. Peter,
Okay.
you're online now? Great.
Yes. Okay. So you addressed the interaction of multiple margins for our example, yes, you can do that by not performing a local sensitivity analysis. Instead, you have to conduct a global sensitivity analysis. Then you can analyze how the different margins, in our case, uncertainties, interact with each other and influence the output signal of the sensing machine elements. So you can do that, of course. I hope this answers your question.
Yep. Thank you. Thank you for that. Thanks.
That's good. Then Leah has a question for Patrick.
Yeah, I just wanted to know if you can also apply your conclusions for the aluminum foam sandwich also to other materials, or didn't you check this by now?
Yeah, do you mean the conclusions about the selection method or about the guidelines?
Mostly the guidelines.
Yeah, I checked some of them because you can apply them to other sandwich materials, of course, but sometimes there are different parts because for example, when you want to put a screw in the foam, you need inserts, and you also need inserts in other sandwich materials. So some of these guidelines are comparable, but other guidelines like bending angles or other points maybe of joining techniques, you can't compare them. But yeah, I know there are some areas I have to look about, and so it's a good question from you. I think I can go on and check also other sandwich materials or other foams and which of these guidelines are more to use, or which of them you can only use for AFS. Yeah.
Okay, thank you.
That's good. So we had some discussions at the end. That's good of the session. Has anyone else has a question? Maybe if you have some questions afterwards, I think it's also easy to contact the authors. I think all of the addresses are in ConfTour or on the papers. I'm not sure, Robert, if you know when the papers will be published to Cambridge Press. Currently, I see that the papers are not online at all. But
yeah,
I think
unfortunately, I don't know the exact date, so sorry.
Yeah, but I think everyone can see the pre-printed versions in ConfTour, so you have the addresses. And I can encourage all of you to work on your very interesting topics. For me, it was a pleasure to moderate this session. If no one else has a question, I think we can close this session today so that everyone has 5 minutes more time to pick up a coffee for the next session or something like this. I want to thank all of you for the presentations, for the discussions, and good luck during the conference. And your, I think most of your PhD works, very good topics.
Thank you.
Thank you. Have a nice day.
Bye.
Thanks.
Bye.
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 Thank you.